can do it. Come on. It's not hard. Ah.
Refresh the page.
Get back. Cool. I should avoid swearing in a language, man. Especially when I'm on camera. Okay, so
Swear anytime.
so is it working? Okay. Okay. I'm sorry, I can check. Because the camera is not working, and so we have to do things. Thanks. Okay.
Okay. So we're going to get started here in a couple of minutes, but I want to see if there's any questions before we get going. Anybody have any questions about like the homework? Anybody done the homework yet? I just realized that you couldn't submit it. We just fixed that. Yeah.
So if, for example, like we implement something, but then the error is larger than what the notebooks says the error should be, like how much of a window is there before we're just
Oh, the window's already built in, so something's wrong. Yeah, you should be able, like in all these things where it's like comparing, like in those cases that's comparing your gradient calculation with like numerical gradient or loss. Yeah, like if it's not within the threshold determined in the notebook, something is not right. Yeah, you should, correct answers will get below it. And it's maddening because like you can get pretty close, which I guess you found out. Okay, so homework is due a week from tomorrow. Alessandro told me that a bunch of you come just like, I don't know, like how to do Python or something like that. And you come to him for help, which is fine, but there's like tons of Python like tutorials out there. And there's like lots of stuff out there to like do some of the basics that are needed for this. And also, there's like tons of people in this class who probably know a thing or two about Python or could help. And so Alessandro asked if I would just have you make sure you introduce yourself to the person all around you. So like look at nearest neighbors here. Like this is K equals 3 nearest neighbors. Just like introduce yourself and say, hey, I know Python, or hey, I don't know Python, or hey, I'm a machine learning expert, or I'm not a machine learning expert.
So you didn't stand for his section? It's really easy. It was the first thing that I learned when I was school, but I didn't use it for like years
Okay, is everybody friends? Everybody's great friends now, right? Good. You hopefully, I mean, obviously you don't need to have it figured out yet, but hopefully you're starting to think about the 1 or 2 other people that you are going to form a group with to do your final project with. So it is required that it is a group effort. So it's groups of 2 or 3. So it can't be one person alone. It can't be 4 people. It's got to be groups of 2 or 3. So you're figuring it out now, you know. You don't want to be like that kid who doesn't get picked on, on the playground at the very end. Like, set yourself up. This is like how life works. Set yourself up now for success. Cool. So, yeah, today we're going to kind of like finish up, I guess, the last of the basics for just like neural networks. We're going to talk about activation functions and just talk about what it means to have a couple of layers put together with some nonlinearities in between, what you can do with that. We're going to talk about something really interesting called the Universal Approximation Theorem, which says that very, very simple neural networks can basically approximate all the functions you could possibly care about. It's not quite right, but it's something like that. Which means that like there's always an architecture to approximate the function that is underlying, say, your data, like a classifier going from data to the classes. Now, there's some caveats and things like that, but it's an interesting result. We're going to talk about what it means and what are some of the shortcomings of it and things like that. And then that's sort of like, in my mind, the end of like the intro to just like machine learning neural networks. Next week we'll start into more interesting architectures and convolutional networks and start learning to use things like TensorFlow and start doing some more interesting types of things. But for now, let's go to activation functions. Yeah, I don't know how to do this though. That's the end. I want that one. Oh, okay. Okay, so remember a couple weeks ago we had this picture that the reason we spent this time with linear classifiers is because a neural network is basically just a stack of linear classifiers. With one really important additional thing, that in between these layers we have what are called activation functions. These activation functions are the things that introduce nonlinearities into the whole function from input to output. And they're critical for being interesting models. If you don't have these activation functions, if you have nothing in between these layers, or you might call it a linear activation function, just linear layers in between. All you have is a matrix factorization, basically. So you can think of like your map from input to output being one large matrix, and each layer is a way of like factoring that into matrices of smaller dimensions. That's great. You can think of it as like deep matrix factorization, but in the end, you just have a linear model. You just have a matrix. And yeah, linear models get us a long ways, but all the interesting phenomena in life are not linear, unfortunately. So we need models that can actually model nonlinear phenomena. And the way that we do that in neural networks is to introduce nonlinearities in between each of the linear classifiers in our network. And that's where all the power ends up being, so super important. Why are they called activations? There's lots of funny words in machine learning and neural networks. Why are they called activations? Well, and why are they called neural networks? Well, because there is some sort of like loose analogy to what's going on in the brain. So here's some awesome drawing of neurons with electrical potentials on them traveling along axons. It's totally like this in your brain. It's like neat, sexy. It's great. Brains are cool. So I'm not expecting anybody to become a neuroscientist, but it's sort of worth just knowing what the analogy is here. So neurons come in all shapes and sizes, but like a basic type of neuron in your brain will look something like this, where you have a cell body and there's all kinds of projections coming out of it. There's one main projection called the axon, and that is the message passing branch of the neuron. Then you typically will have lots of branching processes coming off of the cell body as well. These are called dendrites, and these are like the message receiving end of the neuron. And they're super fascinating. Actually, when I did my PhD here at the University of Utah many millennia ago, I did a PhD in math and applied mathematics, and I did like biophysical models of how proteins traffic around different parts of the neuron in the dendrites and at synapses, where axons connect to dendrites and do the actual passing from one neuron, the passing of information from one neuron to the other. In a super simple way of thinking about this, you might say that the axon has some sort of information. We give it some value, x naught in this picture, and it's making a connection with another neuron, axon to dendrite at this connection point called a synapse in your brain. And we might think of that the connection there has some sort of weight to it. So like it's something like the faithfulness or fidelity with which the information from the axon is passed to the dendrite of this other neuron. And so, the information x naught times this weight or fidelity w naught, multiply those together, that's sort of like, think of that as like the information that actually gets passed. And like the connections that neurons make with each other, they can be excitatory in the sense that like they actually like excite or cause to like to do more message passing, or they can be inhibitory, where they can inhibit the neuron from actually passing information. And you might think of that as like being encoded in the weight by like the sign, being positive or negative or whatever. And you might say, okay, well, there's all kinds of synapses being made, so we might have this bit of information from neuron 0, and then another one from neuron 1, and then from neuron 2, and these all sort of get integrated together. All this information, and there might be some bias term, be some like background activity of the neuron, and that all together might represent like what's happening, the information being integrated at the cell body. And then this idea of activation is neurons are sort of digital in the sense that they like fire, like they don't just pass continuously the information from dendrites to axon. They sort of need to build up electrical potential within the cell body, and then once a certain threshold is passed, then there's like what's called an action potential. Basically, this potential travels down the axon and goes out to the synapses that it's made with other neurons. So there has to be some sort of notion of like being activated or like crossing this threshold. So this is where the name activation comes from. So in the simple model, it's a linear kind of combination of information in the cell body. But at some point, there has to be something else that's saying like, okay, now we're finally going to fire. So these are typically represented by nonlinear functions. In particular, sigmoids are very popular in these kinds of models. And the reason is that they sort of go from 0 to 1. So it's like 0 I'm not firing, 1 I'm firing, or you might scale this a little bit, saying like maybe this represents the firing rate. So like they don't just like neurons can't just keep like firing and firing and firing. They're first of all they're biological, so they only have a finite amount of energy or a finite amount of potential, so they can't just keep firing. So at some point, like the firing rate would saturate, and so these sort of have properties like that. Sigmoids are really popular again in doing this. So like sigmoid is like the quintessential activation function. Although we'll find out that it's like the worst activation function you could use with computational neural networks, and they're never used. In fact, they shouldn't even exist in deep learning frameworks, although they're always there for, I don't know, whatever reason. But you should never ever use one, and we'll talk about why in just a second. But this is kind of like where the language comes from, and this is like the loose analogy of what we're doing in neural networks. We sort of have these connections between neurons. You can think of each node in the network as being a neuron, and it's receiving information from neurons before it in the network, and it's passing information onto neurons after it in the network. But really, don't ever talk about neural networks as being like a brain, because it's so not a brain. Like I was saying, there's tons of different types of neurons. We'll usually only have like one type of neuron. Dendrites, yeah, they perform tons of really amazing nonlinear computations. We are just like combining, we're just like doing a matrix vector multiplication. That's pretty not interesting, right? Synapses, yeah, they don't have a single way. This is like my dissertation is all about how this is done biologically. At least modeling of computation. It's like synapses are super dynamic. They change their ways all the time. They do it in response to what's going on around them. So it's not just like there's a single weight, but whatever. And yeah, rate codes. I didn't spend time with rate codes, but like this patterns of firing that you get from these types of models is probably not accurate or adequate to be able to like model everything that's going on in the brain. So that's where the brain analogies should stop. So we'll continue to talk about neural networks, but that's just a name. That's a historical accident. They're not brains, and they never will be brains. Will they be able to do computations like brains? Maybe, but they're not brains. Okay, so really, activation functions can be anything. They just have to be some sort of nonlinearity. Certain activation functions are better than others for reasons that we'll hopefully start to make clear now. But really, you just need to like throw nonlinearity in there. So sigmoid is like the quintessential one that we're quickly going to say why we don't use it. Then there's a whole bunch of other ones. So this tanh, this hyperbolic tangent, looks a little bit like a sigmoid. Kind of has a little maybe better properties. If you look at it, and maybe you can see why, like it being zero-centered, whatever. The most popular one now, and the thing that really has allowed neural networks to be trained in like adequate time, is this thing, the rectified linear unit ReLU. And it's like the simplest nonlinearity you could possibly imagine. It looks like the hinge loss, and it really is that, right? It's just the max of your output from your neuron with 0. So if your output is positive, you get the output. If it's negative, you get 0. So this is almost linear, except when it's negative and it's 0. So like really close to being linear, but not really. And yeah, like this innovation is really one of the important things historically in getting to where we are with deep learning. There's tons of variants on ReLU. So one of them up here is this leaky ReLU. So instead of it being 0, when it's negative, you have this. You see this max. Instead of that term being 0, you have this 0.1x. So what that turns into is you have, instead of this branch when x is negative being 0, you have it being like a much shallower slope, but it's still a line. And we'll talk in a bit about why that might be interesting to use. There's something sort of like that, this exponential linear unit. ALUs, these ReLUs, leaky ReLUs, ALUs. Gotta get the LU in there. This is sort of like that, but it has an exponential behavior in the negative region. So sort of preserves this kind of feel to it. Like the leaky ReLU, you have non-zero activation in the negative region, but I don't know, whatever. And then there's one that's like totally not like all these. It's this max out, which is basically like you learn basically 2 sets of weights, and you take and you just have linear output, and you take the one that's largest. So you get this nonlinearity through the max. So it's like two linear functions, But by combining them with max, you get some nonlinear behavior. And a really natural question is to say, like, well, what do I use? Well, nobody knows the answer to that. Just don't use sigmoid. Here's why. So, like we talked about, why is sigmoid great? Or why would people even start thinking about it? Well, it smashes. So it has these two regions of behavior. So like near x equals 0, you've got basically linear behavior. Like that's essentially a line in a region around 0. So that's good. Like linear is really good for a lot of reasons. Like computationally, it's efficient, and it's easy to understand. It's easy to understand what the mappings are doing. So we kind of want linear stuff to still exist, but we need to have some nonlinearity so we can model nonlinear phenomena. So here is an idea, right? It's like let's have a function that basically is like linear in a region around 0, but then saturates to like 0 and 1 in this case. I already mentioned the analogy with firing rate. So what could be wrong with that? Well, there's a couple of problems. So one is, this is really, really important. So if you think about the gradient in a sigmoid, again, in the region around 0, this is like a linear function, so you have this nice constant gradient. But as soon as you start to get into these regions where the function's being squashed, down and it's approaching -1 or 1, the gradient is going to 0 in both directions. Now remember, all of our learning depends on gradients. All of our learning that we're doing depends on propagating information from the loss function all the way back through to the beginning of the network via gradients. And if we have small gradients, we're going to have a big problem. Because really quickly, that signal that we're trying to use to walk down the gradient is going to be so small that we're going to be taking tiny steps, and we're never going to get anywhere. We're never going to learn anything. And this is one of the main issues with sigmoids and with these saturating functions in general. Here's a little illustration of this. So, if we're thinking about, here comes, like we talked about last time using backpropagation, here comes our upstream gradient, it hits our sigmoid gate, and then we use the local information that we then backpropagate to the next neuron. So when we're at 0, this is fine. We've got a non-zero gradient, it's nice and it's big, we're going to be able to move information along, but when we're either in the -10, so in this case, with this particular choice of sigmoid, if we're down here in this region or up here in this region, this is essentially 0. So this gradient right here is essentially 0. And learning cannot happen. Must have gradients to learn. What else is wrong with this? Well, it's not like a huge problem, but it's also not super pretty. But sigmoid outputs are not zero-centered in the sense of like, if you think about this, the outputs here are always positive if you use exactly this function. It's always positive. And that might not seem like a bad thing. And actually, it's not that big of a deal. In fact, ReLUs are like this, and ReLUs are very popular. But there is something to think about with it. So what happens to the gradients when you have just positive outputs? Again, this is not that big of a deal, but basically your gradients are just always going to be positive or always going to be negative. So what that means is like when you're taking steps, you take steps. So you can't really take like mixed steps. You have to take these sort of zigzaggy steps, which can also slow down training a bit. But again, it's not really that big of a deal. Again, because ReLUs exhibit the same behavior. Also, a problem here is that you have to you have to compute an exponential here, right? There's an e to the minus x up there. So that's fine when you're just computing one of them, but like if you've got millions of weights and so millions of neurons, and you have to calculate this activation that's got an exponential in it. It can slow things down. And again, it's not that big of a deal, but kind of a big deal, especially if you're training larger networks. So then when someone's like, oh, well, there's Tanch. So Tanch has got the same problem as the sigmoid in that it saturates as you move away from 0. So again, you're going to have a hard time training. You're going to have a hard time learning because your gradients are going to be small if you end up getting in these regimes. It is zero-centered, so I guess that's nice. We can get some mixed gradients, and we can actually don't take the zigzaggy type steps, but importantly here we have this, and also Tanch is made up of exponentials. So we have to evaluate a bunch of exponentials as well. So not really a great innovation, but Tanches still are used. So like when you need to actually compress your output into a finite interval, like basically have a min and a max to it, Tanches are still used, and there's reasons that you might want to do that, but they're not usually like the workhorse. Like in all your layers, like this, what typically occurs here is like maybe this is like you have a final layer that's got a Tanch to it, but everything else before there's something else, so that you can learn. You're helping yourself learn along the way. Okay, so onto this ReLU. So this is, even though it's super simple, this is like a recent innovation. You can see the date on that paper. People just didn't even like think about it before then, I guess. I don't know, or at least they didn't publish on it. But like, this is now basically like if you pick up like any convolutional network that's got many layers, basically every activation in it is a ReLU. So yeah, why is that? Well, it's basically it's because it's like basically linear, except for when the output's negative. And linear, like we're purporting linear, and we should because we can't the important phenomena are linear, but like computationally linear is really good, right? Linear, so computing the max here with itself in 0 is like a really simple operation, right? So computationally, this is super efficient. When your outputs are positive, then you're in a linear regime. So like the gradient is always, you have this constant gradient. So let me be careful. It's not constant with respect to x, but the point is that like you have this guaranteed non-zero, non-saturating gradient. And it converges much faster than using things like sigmoids and Tanch, and I honestly don't know where the 6x came from there. But the reason for it is because you're basically in a linear regime, and like linear convergence, like in these iterative processes, is like it's like the power method. Remember like the power method for yeah, go ahead.
So does it ever happen that the value of x, since like max of 0, x, becomes so large that it overflows the integer that's, let's say, the 2-bit of 64-bit? What happens in that case?
You're saying like the output's so big.
Yeah.
Yes, you can get what's known as exploding gradients. It's hard to do with the ReLU because of the 0 region, the negative region. Yeah, so following up on that and what I was just saying, putting those two together. So if we just had a linear activation and we were doing this iteration, it's like in the power method. Remember the power method? This is like a way that you can compute the largest eigenvalue of a matrix. If you just keep applying the matrix to itself over and over, it's like, yeah, you have like a matrix A times a vector X, and if you just keep multiplying that by a and by a, what happens is that x, or well, the vector that you get at every step is basically converging to the largest to the eigenvector of the largest, associated with the largest eigenvalue. And that's really great for a lot of reasons, but it's really bad too, because really what's happened during that time is that you've made this vector really, really, really long. So like kind of getting at the overflow question you had there. Yes, it's converging to that vector, but it's converging to that subspace, that linear subspace spanned by the eigenvector. But it's getting really long in the case where the eigenvalue is greater than 1, or the absolute value of it is greater than 1. And it's getting really small, going to 0 in the case that the eigenvector is, or the eigenvalue is less than 1 in absolute value. So when you add this, you in many cases avoid both of those scenarios. You get like some benefits of it where you get this efficient computation and moving towards like the dominant behavior in your system, but you prevent yourself from like overflowing or underflowing in the computation. And it's not like perfect, like you can still get yourself into funny scenarios where this will still happen, but it's much harder to do. And yeah, and they're super popular and they're everywhere. And it wasn't only 6 years ago that the world started using these things, so that's pretty amazing.
So for all of these activation functions, there's just like finite advantages and disadvantages. It's not like one activation function fundamentally cannot learn problems that another activation function can learn, or is it that the case?
I don't know the answer to that. I don't know if anybody does. When we do the universal approximation theorem, it's going to be for sigmoidal-like activations, which is kind of funny when you think about it because we don't use them anymore. But yeah, I don't know of a result that's like what you're suggesting. Yeah, so it's not all roses with ReLUs. Obviously, it's not zero-centered, which, again, you're getting, you're having sort of this zigzaggy type behavior in gradient updates. And what happens basically in this is, I think I have the next slide. I have this picture. So it's asking like, what happens when the gradient's 0? I have a couple pictures here, but what really happens is basically like stuff was only happening, interesting stuff's only happening in this positive cone, in whatever dimensional space you're in. And as a result, like what ReLUs tend to do for like a classification problem is like chop the space up into like hypercubes, where this, each cube would correspond to a label, or yeah, each cube would correspond to some sort of label. And maybe you can kind of see it like, so let's see the next slide, but looking at this in the same way, if x is in the positive region, so if x is equal to 10 in this case, we're going to be back propagating good signal of the gradient. When it's at minus 10, there's going to be no signal. And when it's 0, well, it just depends on what decision you made at 0 to have it be, if the max, if the gradient there will be coming from the right or coming from the left. I think usually it's just coming from the left, it's just a 0 gradient. So also no information passed there. Here's this picture I was thinking of. So, ReLUs are only active like in this positive cone. So you think of the plane, you're just working this two-dimensional problem. The positive cone is just where there's everything, where both of your entries in your two-dimensional vector are positive. So only stuff is happening there, but everywhere else it's not happening. So this is what I mean by this sort of cuts up the space. You have your bias as well that sort of puts these different pieces into different parts of the space. And when you combine them all together, you get really interesting and important on your behavior, but it is sort of strange that it's only active in the positive space. And as a result, like the way that learning typically happens is you want to make sure that, I think I actually say this somewhere, yeah. You actually want to make sure that when you initialize these things, that you don't initialize these things to have for the weights to give you a lot of zero activations to begin with. Otherwise, you're going to have a really hard time getting started learning. Usually there's some sort of positive bias in the initialization to allow you to start learning.
So my question is, if x is negative, then the value is basically passing in 0. Shouldn't it pass a negative value? Ideally, in the sense that it should penalize, since we have a negative value, it should penalize the answer. Don't do this, you need to go to the positive side. So it should penalize somehow so that it converges to the right direction?
Well, the activations don't know anything about the right direction, right? It's the gradient that knows about the right direction. So, the thing you're kind of thinking about, I think, is treated by like the leaky ReLUs, which we'll talk about next, and the exponential linear units, the ALUs. But this still learns a ton, and it's not activations. Again, are just like I get my linear output. I'm at whatever layer I'm at. I take the input from the previous layer. I compute my linear function, and then I do something to that output. And here you just say if you're negative, you're a 0 value.
But don't the, like from the example you just gave, like the slide previous, it seems like the activation nodes in our graph, they're part of our graph, right?
Yep.
So they still backpropagate?
Well, they backpropagate, but if you're in the negative region, your gradient there is going to be 0.
Well, that's what so kind of following up on this is
Yeah.
like, it seems like it's backpropagating no information when it should be saying, hey, we need to adjust something. Is that the right interpretation, or is that misunderstanding?
Okay, yeah. So, I mean, there is information there. It's saying, hey, like, it's saying you're not positive, like, you're not contributing anything if your value's in here. So it does promote things to be, like, positive, but it can actually use the 0 values to do interesting nonlinear things. It's just that those weights don't get adjusted to change the fact that it's a 0.
Yeah.
Does that make sense?
Yeah.
Now, like it is true. I think what you both are bringing up, that like it seems weird that like no information is being passed, and that's what the leaky ReLU is about. And the ALU is like, okay, let's at least get a little bit of information through. But in practice, ReLUs do the job, and they're faster. Yeah.
So by the same logic, a negative ReLU should perform the same job, right? I mean,
Yeah.
it's symmetrical.
Yep.
It should perform.
That's right. Everything would just have different signs. That's exactly right.
So I was wondering, how does this compare to the SVM function that we have? Even that, even if it is negative, it is 0.
Yeah.
It doesn't care.
Right. So it's very similar, right? It's basically the same form. You just what you're taking the max of, instead of it just being the output of a function, or the output of this linear function. It's actually you're taking the score. So again, it's just output from some linear function, but its job is to do something a little bit different, which is make the one score larger than the other scores by a certain margin. So it's very similar. It's trying to put things into this regime. But if it's over here, then you have some sort of non-zero loss, and you have some non-zero gradient, and that's pushing things to be back into that regime for the loss. But remember, these are like intermediate computations on the way to the loss.
So the difference being that it's not maximizing any difference between the
Right.
SVM tries to maximize
Right.
a certain distance, but this is just trying to put it in a specific region.
Yep. I mean, this is just saying like, if you're 0, that's don't change the weights associated with that. At least you won't get any signal from this particular neuron to change that. And if it's positive, you'll get some non-zero signal to change it. Yeah, it's funny. Like teaching it in a class because it's just like machine learning gospel at this point. You just do RAIDs because they're efficient and they totally work. And every once in a while, like a new activation function comes out, and there's like some paper about like how it blows everything out of the water. Then like nobody can reproduce it, and no one starts using it, and everybody just goes back to RAIDs. Again, because they're fast and they do the job. This is important. You need to make sure that you've got like enough gradient when you get started so you can actually learn something. Otherwise, there's going to be a problem. So anyway, Thinky ReLU, yeah, green's all around. Has all the properties of the ReLU, and then when you're in negative, you get a little bit of signal. Again, if they had just made this the same slope, so if this was just x and not this max thing, then it would not be nonlinear, it would be linear, and then you wouldn't get nonlinear behavior. So this is like, again, something almost linear. There's just changing the slopes is a little bit different. So yeah, it's great. It doesn't die anywhere. There's gradient everywhere. You can even control, whatever the slope is over here. You can make that a hyperparameter in what you're doing, and you can train it, but honestly, it's not really done. You just use ReLUs. I mean, people do it every once in a while, but it's just, like, in general, it's just ReLUs. Everywhere you look, it's raining ReLUs. And yeah, then someone says, oh, how about let's try this? It's great, works. It's not as fast as a ReLU, mainly because you got an exponential, and you just use the ReLUs. Max out, yeah, like, pretty interesting. Ian Goodfellow introduced it, so he's kind of a big name in deep learning. So people start to think, oh, well, if he introduced it, I probably should use it. But the trouble is that you got like two sets of parameters now. And that's, for these big networks, that's just, you're going to go from 25 million parameters to 50 million parameters. That's a lot of parameters. So it's rarely ever used, but hey, now you know about it. Yeah, so in practice, use ReLU. You can try things out. You probably should try things out. You need to get to the same point as like everybody else in this world who does this day to day, is like believe that basically ReLU is all you need. But yeah, don't use sigmoid.
So just a clarification, when we were saying it kills the gradients, like I'm just thinking about this in terms of backpropagation.
Yep.
So once you hit a node and it says, okay, 0 is getting backpropagated,
Yep.
does that continue to be 0 all the way back through the chain?
So contribution from that node is 0, but you see there's lots of stuff. There's lots of signal coming into each neuron, right? Because you're making lots of connections with other neurons, right?
So if you had like one node,
Yep.
this is totally practical, then it would kill everything.
Yes.
Okay.
There would be no learning. It would be sad. But yeah, we have lots of neurons, and we basically like fully connect everything. I mean, convolutions are all about not fully connecting everything, but there's still like tons and tons of connections. So yeah, even just because one node is not going to contribute to the gradient in the backpropagation doesn't mean that other nodes won't. But yeah, like if all of them didn't contribute anything, we're back in the same boat. But luckily, that doesn't happen in these networks that we're going to steadily be using. Okay, so let's take a vote. Sigmoid? Raise your hand if you want to use sigmoid. Okay, one brave soul wants to use sigmoid. The rest of you are listening. And who wants to use ReLU? Yay! Who's thinking like, what Thinky ReLU looks good? Yeah, try it. And then compare it with ReLU. And compare both your accuracy or whatever it is you're measuring is your metric of determining how well you're doing. And then look at the time it took to train to get to that value and just see that ReLU wins. It's just empirical, and it's just the way it is. Okay, fully connected neural networks. So up to this point, our score functions have just been these linear functions. Like they're these very simple linear score functions with different types of losses. But now we can have layers of these. So this is a two-layer network with ReLU in between. You have W1 representing the weights of like the first layer, so that's times your input x. Then you apply your activation function. This is applied, by the way, entry-wise. It's every single entry of that vector, W1 times x, you max with 0. And then whatever vector comes out of that, you multiply that by another matrix, and then your loss function. And voila, you have a neural network. Yeah, you can even look at a picture of it. Like that. It's super great. You actually are doing this in your homework, so you still get weights, right? You just have like layers of weights. So your first layer of weights is still going to have some sort of look to it. And especially in a shallow network, it still might look a lot like the linear stuff did. But if you then go to like the next set of weights in your second layer, you're going to start to see things that don't really make sense anymore because it doesn't. Yeah, it's hard to interpret them. Usually, like when people try to interpret what's going on, you look at the first set of weights, your first layer of weights, and that's like the last time you really can like make a connection from the weights to the data. After that, it's really hard to do. You can talk about like there's lots of tools now for talking about like as you move through the network, what regions of the filter maps. Now I'm starting to use language that we haven't used that in the class, but like what regions of these weights are contributing gradients and learning and things like that. But really, it's just like this first layer of weights that is like the interpretable one. But yeah, you can just keep iterating this, right? So if I want to have a 3-layer network, I just do that again. The output from that second layer, I just do the same thing and choose my ReLU, compute the activation, and then multiply that with our linear function, and then apply the loss. So it's pretty simple, actually. Like the code is pretty. The ideas are pretty simple. Like do a matrix multiplication, then apply an activation, then do a matrix multiplication, and so forth. It's pretty simple in the end. It's sort of strangely simple, actually. And you get to do this. It's like the final of the 4 notebooks. The final notebook is actually basically doing the same thing you did for softmax and SVM. You now have a 2-layer network. And it's really exciting when you get it to work, because it's like, wow, we're doing neural networks. Can't call it deep yet because it's only 2 layers, but it's deeper than the softmax, this SVM examples. So yeah, good luck on that. It's fun. At least I think it's fun. Yeah, just a little bit of discussion around like naming. So I think back like when these were first being researched, people would think a lot about like how to arrange the neurons and like which neurons to connect with which neurons in the next layer and so forth. But basically, these days that's like none of that stuff's done. Basically, everything from one layer gets connected to everything in the next layer, and that and so forth as you move from layer to layer. And that's why these are called fully connected networks. They're fully connected. Everything from here is connected to everything in here, and everything in here is connected to everything in here. And if you have more hidden layers, then that pattern just keeps propagating. The language around here is. When we talk about like how many layers, like a 2-layer neural network, the input layer is never considered a layer. I mean, we call it a layer, but it's not considered a layer. You're talking about your network. Like a 1-layer neural network is the stuff you've been doing in your homework, except for the last notebook. But A two-layer network is basically one hidden layer and then the output layer. Or a three-layer neural network has got two hidden layers and an output layer. So when we talk about like, a deep residual network having 152 layers, and there's input and then 152 different layers below. They are not fully connected. That would be huge. That would be a lot of weights. Way more than probably atoms in the universe, I guess. But these small networks we often think about as being fully connected. And they're super simple to implement. Like we were just saying, like you just keep applying this, matrix multiplication, activation, matrix multiplication, activation. And see this, there's a sigmoid in here, that's bad. This person doesn't know what they're doing. Okay, so like why neural networks in the first place? So again, like I'm not sure exactly what the years were, but it wasn't that long ago that if you said you were doing neural network stuff, like people would just be like, you're an idiot. Like, don't you use random forests? Like, they're so good. And you can't train these things. They take too long, and they're never as good as a random forest. So you're an idiot. Why do you use this? And for a long time, like the neural network people were just like, yeah, I guess I am an idiot. But they believed in the neural networks for a number of reasons, and one of them is this really, really interesting idea called universal approximation. So I don't know. I think computer science has probably got a lot of approximation theorems, and some of them are universal. But the idea here is that it turns out that neural networks can actually basically implement any function, any continuous function, and a whole host of discontinuous ones as well. There's a pretty nice way of proving that neural networks with just a single hidden layer can approximate any continuous function on a bounded domain. That's pretty powerful, actually. Like, if you can come to a problem saying like, okay, machine learning in a lot of ways, especially supervised learning, is function approximation. You have inputs to your function and that you've observed, and you have the outputs that you observe. And that's your x and your y that you've been using here. So you're trying to learn or approximate the function that takes you from your inputs to your outputs. And if you can come to it with a model that can approximate it to whatever degree to whatever level of error you like, then that's pretty powerful. And so this is one of the things that made neural network people stick with it. They're like, yeah, but your random forest has no guarantees on what it can, that it can approximate anything. So there's like lots of proofs, different ways of proof. I think there's one more before that's a little more esoteric. It wasn't really clear that it applied to these kinds of things, but this is a statement of a theorem like this. So let sigma be any continuous sigmoidal function. We'll talk about what it means to be sigmoidal in a second. But think of this as your activation, okay? Then finite sums of the form, and you have a finite sum. That looks a lot like what we've been doing. Here's a linear map, followed by an activation, followed by some additional scaling here, so like another linear map. These functions, these sums, these functions, they're dense in the set of functions, the set of continuous functions. The in is the hypercube of in dimension n. But the proof could be extended to any finite domain or bounded domain in any dimension. So in other words, if I'm given one of these continuous functions and some error tolerance, epsilon, then there is one of these sums, choices of y, theta, and alpha, where I can guarantee that point-wise my finite sums are within epsilon of the function I want to approximate. So that's pretty cool, actually. It's a pretty amazing result because, well, let's see. I lost this. There we go. Like I said before, this isn't every function, but there's a heck of a lot of functions there. And even the functions that you typically want to model but aren't continuous, they're very often piecewise continuous. So this very easily extends to being able to approximate piecewise continuous functions. And yeah, so like a ton of stuff, like a ton of phenomena in the world, we can model, and we can do it with a single hidden layer. So this isn't even like a deep network. The guarantee is that we can find a network that can do this with a single hidden layer. So let's look at the form of this thing real quick. So the x there is our input layer. The x in that finite something, that function g. The y and the theta, they are our parameters, our weights for that first layer, right? So the y is what we would normally call w, or what we happen to call w, and that theta is what we've been calling w, the bias. That sigmoid is the activation. That gives us the outputs in our hidden layer. And then finally, we have just a finite sum, or we just have these scalars, so it's like another matrix multiplication to our output. Yeah, so that's it. Like in this single, this is a two-layer network so it's got a single hidden layer. We can basically approximate any continuous function. How is that done? There's a link. There's a link on like the syllabus to this. I think it says something about like visual proof. It's really fun to go through. They've done a really nice job of like allowing it to play with these ideas. It's a nice write-up, and then like there's actually like reactive JavaScript in here where you can change these neurons. So going from input to 2 neurons, and then those combine to an output. You can make these types of outputs. You can make these sort of stepwise outputs. What's nice about the web page is that it gives you a really good intuition for how these things are made. But the point is that you can make these things with 2 sort of sigmoidal things. Oh, I sort of passed it up earlier. Wait 1 second. Yeah, the sigmoidal, they take a sort of loose definition of sigmoidal, but as long as it's like approaching 1 as t gets large, and approaching 0 as t gets negative, then that's a sigmoid. So there is thus sigmoid, which does the nice exponential thing in between, but any function that does this and it's continuous, you can make this happen. But again, the point is that I can pick parameters in this small sort of subnetwork, and I can get outputs that are like this sort of step, this like tower thing, this step. And you can sort of imagine 2 sigmoids kind of coming together and creating this, right? Like one sigmoid like this, another sigmoid like this, and you can get these kinds of behaviors. And once you can build things like this, then you can just continue to put these units together, and you can take any continuous function, and you can start to make another function that is somewhat like it. And I can continue to like make this region here over which this step-like thing is happening, step up, step down. I can make that smaller, and I can adjust that height. I just keep doing that until the yellow piecewise function is, within epsilon of our original function shown there in blue. So yeah, so with pairs of hidden neurons, I can make these step up, step down things, piecewise functions, and I can put those together, and voila, I get whatever function I'm trying to approximate. And if you just go to because you click on that link, visual a visual proof, I think is what it says in the syllabus. And you just read through it and play around with it. It's really fun and really builds your intuition about this. So cool. So great result, right? Who's excited? John is excited. Yeah. What's your name? Yeah.
Eric.
Yeah. Eric's excited. I'm excited. Except that I know something about this that's not so exciting. So it's not really all that exciting. Because basically, I should say it requires 2 neurons for every small volume of the space. So if you're going to build up a function like this piecewise in this way, and you're trying to like model really wiggly functions which are continuous, that live in this function in this function space, then you basically have to have a ton of neurons. And not only that, like as the dimension of your space grows, that means like the dimension of your volumes that you sort of need to set these things over, those get exponentially larger, and you need tons of neurons. So it's not really, in this paper it's really criticized that it didn't bring this point up, because it's now subsequently it's what everybody complains about. But you basically need in this layer just like an exponentially huge number of neurons. So even though you can approximate every function in every continuous function on a bounded interval, like computationally you can't do it. And it's really not clear which functions you can computationally model in this way or approximate in this way, and which ones you can't. So yeah, so Cyberno got our hopes up, and then we dashed them with thinking. But all is not lost, it turns out. So the important innovation in neural networks, besides RADUs, is this notion of using depth to overcome the need for an exponentially large number of neurons in a single hidden layer. Every time you add a layer, it's like you're, in some sense, like logarithmically decreasing some sort of computational cost. Like how much depth you need to do to model certain kinds of functions and certain hypothesis classes and things like that. We're not going to go into it here, but just know that basically we still have a kind of universal approximation property with neural networks that occurs when we, like, in some sense, factor that single hidden layer down into many layers. Research and stuff, back when it was not cool to do it, you could only train these fully connected, they only had these fully connected networks, and they were using like sigmoids. So as soon as it got kind of deep, you'd have saturating gradients, and you couldn't learn anything. So you couldn't, like you couldn't show that you were approximating these things because basically you were using like the wrong thing, like the wrong activations. So why did it take till 2012 for someone to come up with an activation that seemed like overcome a lot? I don't really understand that, but that's what happened. And we all get to stand on the shoulders of giants who sort of went through the pain and the shame of like continuing to do neural network research when it wasn't cool, to then show up in 2012 and win like very handily, all the visual all the image visualization competitions. And yeah, and it's mainly because of depth. Mainly because people figured out techniques like architectures, activations, and certain types of training techniques to be able to train deep networks. And deep back then was maybe like, I can't remember what that was, about like 8 or 9 or so. And now, of course, people are training networks that are hundreds of layers deep. So, yeah, pretty amazing. Okay, so I want to give you some sense of this. So questions on any of this so far? Okay, this is a really fun thing to play around with. And again, I think there's a link in the syllabus for this week for this. So somebody built this cool web tool. So it's JavaScript, so something is running. I don't know exactly what it is in the background, but it must be TensorFlow because it's on the TensorFlow site. But you can play around with this thing and really get some sense of like what's happening in these simple neural networks. So how this works is there's 4 data sets you can choose from. Let me see if this might not be. So there's 4 data sets you can choose from, and these are classifiers that we're learning that we're learning here. So there's neural networks that are defined here, and we're trying to classify the 2 sets of points here. So you see, there's 2 sets of points. There's stuff in the center, and this like concentric ring around it. There's also this data set where you have like the 2 pairs. Remember, like these were some of these sets that we said linear functions or linear classifiers couldn't learn. There's a really simple linearly separable set to play around with. And here's a really difficult spiral set to work with. But the point is that there's 2 classes. There's the blues and the oranges, and we're trying to learn a classifier that can accurately predict the test set. And the test set is just, actually there's a button here to show the test set. It's just a sample from exactly the same distribution of things. So let's just start with this one here. So you get to decide what features you're going to input into your network. You get 7 options here. So one is, well, 2 of these are just x1 and x2, right? So the x coordinate and the y coordinate. So those could be the 2 inputs. So you'd have, for each point in this data set, you'd have its x1 and x2 coordinate,